students, let us start with Laplace differential equation. Let phi of xy be a real valued function of x and y, then partial differential equation is dabba square phi upon dabba x square plus dabba square phi upon dabba y square is equals to 0 is called Laplace differential equation, that is phi xx plus phi yy is equals to 0. The operator dabba square upon dabba x square plus dabba square upon dabba y square is known as del square in bracket del operator. Okay. The above Laplace differential equation can be written as dabba square upon dabba x square plus dabba square upon dabba y square of phi is equals to 0. Next definition is harmonic function. Real valued function of two variables x and y is said to be harmonic in a given domain of xy plane or xy axis if throughout that domain has a continuous partial derivatives of first and second order and satisfy the partial differential equation hxx of xy plus hyy of xy is equals to 0. Okay. Let us see theorem. If a function f of z is equals to u of xy plus I into v of xy is analytic in domain D. Analytic means what? It is a differentiable in D. Then its component functions u and v are harmonic. Harmonic means what? Uxx plus uyy is equals to 0 and vxx plus vyy is equals to 0. Let us see next definition, harmonic conjugate. If two functions u and v are harmonic in D and their first order partial derivative satisfy CR equations throughout D, then v is said to be harmonic conjugate of u. Two functions u and v are harmonic in D and their first order partial derivatives satisfy CR equations throughout the D, then v is said to be harmonic conjugate of u. Okay, let us see some example. Show that u of xy is harmonic in some domain and find harmonic conjugate v of xy when first is u of xy is equals to 2 into x into 1 minus y. Okay, see solution. Here u of xy is equals to 2x into 1 minus y. Okay, differentiate above equation with respect to x. So ux is equals to 2 into 1 minus y. Again differentiate with respect to x, we will get uxx is equals to 0. Similarly, differentiating u with respect to y, we get uy is equals to minus 2x and also uyy is equals to 0. So we will obtain uxx plus uyy is equals to 0. So u of xy is harmonic in D. Okay. Now we have to find the harmonic conjugate v of xy of u. For this consider dv is equals to dabba v upon dabba x dx plus dabba v upon dabba y dy. Call this equation 1. Since ux is equals to 2 into 1 minus y, which is equals to vy, this is by CR equation. Uy is equals to minus 2x, which is equals to minus vx. So we will get, this is again by CR equation. Vx is equals to 2x and vy is equals to 2 into 1 minus y. Put these values in equation 1. We will get dv is equals to 2x into dx plus 2 into 1 minus y into dy. This is a differential equation in the form mdx plus ndy. Here m is equals to 2x and n is equals to 2 into 1 minus y. Differentiating m with respect to y and n with respect to x, we will get dA by m upon dA by y is 0 and dA by n upon dA by x is equals to 0. Here we will get dA by m upon dA by y plus dA by n upon dA by x is equals to 0. So, we can see here dA by m upon dA by y is equals to dA by n upon dA by x. So, given differential equation is exact differential equation. Okay. So, solution of this differential equation is v is equals to integration m dx, here y is constant, plus integration n in bracket terms are free from x plus c. So, v is equals to integration, here m is 2x. Here this m does not contain any term of y, so m write m as it is. So here integration 2x dx plus integration n, terms are free from x, here n 2 into 1 minus y dy plus c. Okay, solve this integration, we will get v is equals to x square plus 2y minus y square plus c. Okay, this is not equals to 0, which is the required harmonic conjugate of u of xy. Hence, we have f of z is equals to u of xy plus I into v of xy. That is f of z is equals to 2x into 1 minus y plus I into x square plus 2y minus y square plus c. Now we will solve next example. Here u of xy is equals to 2x minus x cube plus 3xy square. First we have to check this u is harmonic or not. Then we will find harmonic conjugate of this u. Differentiating u with respect to x, we will get 2 minus 3x square plus 3y square. Again differentiate u with respect to x, we will get minus 6x. Similarly, differentiating u with respect to y, we will get uy is equals to 6xy and uyy is equals to 6x. Hence, we obtain uxx plus uyy is equals to 0. That implies the function u of xy is harmonic. Now, we have to find the harmonic conjugate v of xy of u. dv is equals to, consider the equation, dv is equals to dA by v upon dA by x dx plus dA by v upon dA by y dy. This is not equals to 0. Call this equation 1. Since ux is equals to here this 2 minus 3x square plus 3y square, which is equals to vy. This is by CR equation. Similarly, uy is equals to 6xy, which is equals to minus vx. So we will get vy is equals to this and vx is equals to this. Using these values in equation 1, we will get dv is equals to 2 minus 3x square plus 3y square into dx minus 6xy dy is equals to 0. Okay. So here m is 2 minus 3x square plus 3y square and n is minus 6xy. So differentiating m with respect to y and n with respect to x, we will get dA by m upon dA by y is equals to minus 6x and dA by n upon dA by x is equals to minus 6x. So we will get dA by m upon dA by y is equals to dA by n upon dA by x. Okay. Hence, given differential equation is exact differential equation. So its solution is integration m dx, y is constant, plus integration n terms are free from x dx plus c. So we will get v is equals to, this is m and here is n, here we will get 0. So solving this, we will get 2x minus 3x cube upon 3 plus 3y square x. So we will get v is equals to 2x minus x square plus 3y square x. X square here is x cube. So which is required harmonic conjugate of u of xy. So we will get f of z is equals to u of xy plus I into v of xy. Put values of u and v. Okay. Let us see next example. Find the harmonic conjugate of u of xy is equals to y cube minus 3x square into y. We will solve this example by using another method. We have u of xy is equals to y cube minus 3x square y. Here differentiate u with respect to x, we will get minus 6xy. Differentiate u with respect to y, we will get 3y square minus 3x square. Since this function is analytic and CR equations are satisfied, so you will get ux is equals to vy and uy is equals to minus vx. Ux is equals to vy, which is equals to minus 6xy. Call this equation number 3. And uy is equals to minus vx. Uy is 3y square minus 3x square. So we will get vx is equals to 3x square minus 3y square. Call this equation number 4. Suppose x is fixed and taking integration with respect to y, we get v is equals to 6xy square upon 2 plus phi of x. In equation number 3, we will keep x is fixed and taking integration with respect to y, we will get v is equals to 6xy square upon 2 plus phi of xy. Where phi is arbitrary function of x. Call this equation number 5. Differentiating phi with respect to x, we get vx is equals to minus 6y square upon 2 plus phi dash of x. That is vx is equals to minus 3y square plus phi dash of x. Equation number 6. Now from equation number 4, this is equation number 4, and equation number 6, we observe that minus 3y square plus phi dash of x is equals to 3x square minus 3y square. This minus 3y square minus 3y square get cancelled. Here we will get phi dash of x is equals to 3x square. So taking integration of above equation with respect to x, we will get phi of x is equals to 3 into x cube upon 3. 3 get cancelled. So we will get phi of x is equals to x cube. This is the equation number 7. Put equation 7 in equation number 5. We will get v is equals to minus 3xy square plus x cube, which is the required harmonic conjugate of u of xy. And the analytic function will be f of z is equals to u of xy plus I into v of xy. Put value of u and v.